In this section, we shall discuss neutral delay differential equation with the delay in the both functions x of t and its derivative x dash of t. So if we see in this equation, a of t, b of t, and c of t, so these functions are given bounded functions. So these function we have to take these function in the start. So these functions will be the given functions. So the function g, if we see the function g, this is a non-linear continuous function. Okay, and r of t is a bounded delay function. If we see, we have given here r of t. So this here we can see r of t here. So this is a bounded delay function. So the last term, the following term, so this term make the differential equation as a neutral delay differential equation. Why? Because the derivative here x dash of t appears with the delay. So you can see that this x dash of t, t minus r of t, this makes the following function, following equation as a neutral delay differential equation. So now if we want to find the solution of this, there is a well-known lemma given below. So this lemma shows that if we want to find the solution of the following equation, then x of t will be the solution of this equation if it is given in this way. So now I state here the following lemma. So assume that the function r dash of t is not equal to 0 for all of t, then we say that x of t represented below is a solution of above neutral delay differential equation. Okay, so here if x of t, because we are taking here we are taking here r dash of t is not equal to 0. So if r of t is r dash of t is equal to 0, then what will happen? We will see here where it is given h of v is equal to 1 minus r dash of t. So this will become 0. It means the denominator will become 0. So what this shows that with this h of v will becomes undefined. Okay, so this term, it means that this condition r of t, what is the physical meaning of this? So r of t is not equal to 1. So this ensures that the delay functions grow the delay function grow slower or faster than the times. Okay, so the neutral terms, so if we see the last term here, this term, this x dash of t, t minus r of t, so this is a neutral term, so does not make a problem with the derivative. So with what this shows that, this shows that the solution is stable. The solution is stable. Now if we take this r dash of t is equal to 1, and if we take its antiderivative, so what we get here? We shall get here r of t is equal to t plus c. Okay, so with this the system, if we put in the equation, so what we will get here? It will becomes here. So 1 minus r dash of t will, r dash of v will become here 0. So what will be the problem here? So then the system of the equations given above, it will become unstable or unbalanced, and the solution x of t will become unstable solution, or it will become ill-defined function, or otherwise on other sense we can say that it is not well-defined solution. Now if we want to link it with the fixed point theory, or we want to find the solution of the equation by the fixed point result, then what we have to do, we have to define an operator, some operator T, okay, which will be defined on the Banach space. So how the operator will be defined? So here you can see x of t, we defined here t x of t. What is the relationship of this with our result basically? So whenever we ask that, we define an operator on the Banach space of the continuous functions. So we know that every Banach space is a complete metric space. What is Banach space basically? It is a complete norm space. Okay. So we have this relationship between the metric space and the Banach space, that every Banach space is a complete metric space. And what is the relationship of the metric space with the F metric space? We have this relationship that every metric space is a F metric space. So whenever we deal with the Banach space, it means we are dealing with the complete F metric space. Okay. So if we want to find how now I try to summarize this. So if we want to find the equation of the solution of this equation 5, okay, so it is well known fact that this x of t is a solution of the above, okay, if it is defined in this way. Okay, now I link it with the fixed point theory. I say that if I defined an operator t x of t, uh, which is defined on the Banach space, if that operator T satisfy the contractive condition of our main theorem, then we can say that by the help of our fixed point result, we can say that the operator T has a fixed point. It means x of t is equal to t x of t. Okay, then x of t will be the fixed point of the mapping, and this x of t will become the solution of the above differential equation. Here we discuss the construction of solution with the help of our fixed point result. It means which things we require to use our result to find the solution of the equation. So if we see in our result, we need the set X. It should be the non-empty set. So here we defined here M eta, which is the set of the continuous and bounded function. Okay. So M eta or ME, this is the set of the continuous functions and set those functions which are bounded. So here there is a correction. You have written here, assume that C denotes the set of the function. Yes, it is correct. But if you write here, assume that C, then whenever you define ME, then you should write here omega belongs to C. Okay. Otherwise, delete C from here. Okay. So basically, omega are the continuous function, and whenever we say that omega of t is equal to e eta of t, so here eta of t, it is bounded and continuous function. So basically m of e or me, this is the set of the continuous and bounded function. It is a non-empty set. Now on it we define the metric d. Okay, so we defined the metric df. If we see in the lemma, df t dash of t, which is the norm of t minus t. So how we say that? It is given in this way. It means the difference, the maximum of the difference of their values. It means if we have t is one function, t dash is another function. So what is this? It means t of x minus t star of x. We will take their values and we will take the absolute of this. What is the maximum value? So this is basically the metric. So if we see that this is the same like the supremum norm, okay. So M M ME with this metric, it is a Banach space. It is also because Banach space, as I asked you in the previous slide, so Banach space is a complete metric space. Okay, so we say that the space ME with this norm equipped with the distance given in this way, it is a complete F metric space. Okay, so in this slide, basically we have three things. One, the set X we defined here ME, okay, which is the set of the continuous and the bounded functions. We have this thing, and we need here the distance. We define the distance in the form of the supremum norm. So here dft t star, it is equal to the norm of t minus t star, which is defined in this way. It means supremum of x of I, t of x minus t star of x. So in some books it is given here f and g, okay. uh, because if we see in the start in the equation, g is given, okay. So we can take here df of f and h, okay. And what it will become, the norm of f minus h, which is equal to the supremum of x belongs to I, which is in some books it is given I is equal to a to b, some closed interval, okay. So f of t minus h of t, so the maximum value and their absolute value, the difference of the absolute value and its supremum. So along with this metric, m of uh, the norm of this becomes the Banach space. So as I linked in the previous, that every Banach space is a complete metric space, and every metric space is a complete metric space is a complete F metric space. So thus we say that ME and D, this becomes complete F metric space.